we don't have very many physicists, women, that is, women physicists. And we don't have really many more oceanographers. And what John Delaney has been working on over the last decade or so, or actually most of his whole career, is finding ways to really learn more about our planet through understanding the function of the oceans. And several years ago, he came to talk to me while I was director of NSF with this outrageous proposal to wire the entire ocean. He called it Neptune. In fact, the National Science Foundation did fund it, and it's now known, I guess, as the observatory system. But the kinds of things that John has done in his career as an oceanographer are really incredible, from being part of the discovery of the deep ocean vents in the Atlantic, which are quite different from the ones in the Pacific, to integrating the ocean characterization and parameters with those of outer space. So without further comment, I'll just say, John, thank you very much for making the trip, especially it's now 24 days since your hip replacement.
That's right.
And flying across the country to speak to us. Thank you.
I didn't walk, I flew. Well, I got to tell you, this may not be something you're immediately aware of, but there are perks to being a token tall white male. I have the men's room to myself. That may not be a kind of perk that any of you are interested in, but I'm still searching. Anyway, I deeply appreciate the opportunity to speak to this group. And I would say that the world that I come from is an ocean of opportunity for everyone. And what I'd like to talk about is the way in which the nature of oceanography is about to shift in a fashion that's going to make it very much like the young lady who spoke yesterday about exploring the cosmos. The democratization of science is at our doorstep, and I'd like to share that with you. Carla gave me some help by refining my title to Next Generation Science in the Ocean Basins, but I wanted to give it a little bit of context in that the oceans are in fact the life support system for the entire planet. Without them, even life on the continents would be virtually impossible. Think Mars. About 3 billion years ago, Mars probably had an ocean in this northern hemisphere, but it's a desert now, and for all of the dreary pictures that come back that look like something leaked down a cliff face, Mars is not a great place compared to Earth. And so we have an ocean on this planet, and it is our life support system. We are as dependent upon the functioning of the ocean as were the lunar astronauts who were bouncing around and hitting golf balls into outer space. Were dependent on their backpacks. That's how dependent we are on the oceans. So in the event that you need to catch a quick nap, I wanted to summarize the entire talk in a single slide. And bottom line is the oceans are essential to life on the continents. They are complex. This is a wrinkle that we need to talk about. They're very complex, and they're changing rapidly, and they're changing unpredictably. That's a difficulty. How do we look into the future? How do we plan long-term if the central heat engine for the entire planet in terms of climatic controls is changing in a way that we have a hard time predicting? Well, there are very sophisticated models, computer models, that are way more sophisticated than they are accurate. So it's an important thing to be able to offer them new kinds of data so that they can eventually become predictive. So the concept behind this is that new kinds of data have to be collected within the ocean in order to make the sophisticated models that we're capable of now actually more and more and more predictive. And finally, The novel technologies that I'd like to share with you today, and others that I probably cannot share with you yet, are going to transform the way we perceive the oceans. And it may, in fact, translate in the time of our children, perhaps grandchildren in my case, when we will actually have to manage almost an entire global system, the planet ocean. I doubt we can do that. I know we can't do it now. We're not wise enough. I've heard people talk about geoengineering, and it's considered anathema by some, and it's considered to be one possibility for hope by others. So let's get into it. When scientists begin doing some problem, obviously all of you have been exposed to this, you choose the system. Well, this is the system. The oceans, the atmosphere, the Earth itself. This is the system of interest. And the bottom line is our challenge is to optimize the benefits and mitigate the risks that are implicit in living on a planet that has basically two energy sources. The first is the one that we know little about in Seattle. Solar energy is not something we experience on a regular basis, but solar energy is the input to the outside of the planet, and it drives ocean currents, moves the winds and the waves, and builds hurricanes. It causes erosion, drought, forces storms, all sorts of rainfall. It's a source of photosynthesis, and it is central to the cycling of carbon, solar energy. I'm a geologist. I'm from North Carolina, and I grew up in the era when Senator Sam Ervin was holding forth in the Senate. He used to refer to himself as a simple country lawyer. I think of myself as a simple country geologist. I did my early studies in the Shenandoah Valley mapping limestones. But the internal energy on this planet drives a host of other processes, and to some extent, these two major forces operate on the surface of the planet and have for 4.5 billion years. So the planet as it stands now, the internal energy drives plate tectonics, moves continents, builds mountain ranges, drives volcanoes, causes major earthquakes, concentrates metal deposits, is a framework for many energy deposits, and it's a source of chemosynthesis as opposed to photosynthesis. So that's the framework. And the human element is one in which humans are clearly rapidly altering the Earth's system and increasing the ocean's vulnerability. This is the ocean we're dependent upon. Increasing the ocean's vulnerability to stresses and perturbations. And the most sensible way to address this issue requires a clear understanding of the organization and function of marine ecosystems. Now, marine ecosystems are really complicated. You can think of on continents, you think of ecosystems as having plants grow up out of the soil, and maybe animals graze on some part of it, or maybe it's a jungle, or maybe it's a tundra, whatever it is. In the ocean, it's four-dimensional, and it's dynamic. And everything that grows in the ocean is supported by the ocean, both chemically and physically. And so there's this unbelievable, and I'll come to it in just a second, unbelievable complexity associated with the phenomenon of the ocean itself. And the marine ecosystems are indeed a fundamental study in complexity, and complexity is something that's really important. It's like trying to understand the human brain in its capacity to be creative. How do you do that? It's such a complex system. Another less elegant metaphor or analog would be the stock market. It's very difficult for many of us to predict the stock market because it's so complicated. Many of the factors that bear on it. Well, the oceans are complicated in spades compared to any of these others. And just to capture some of that, I wanted to share this with you. I haven't got by any means anywhere close to all the processes that are involved, but you can see the rich complexity of all the interactive factors under the sea, at the sea surface, up in the atmosphere. In fact, even the sun and the moon affect the oceans directly, as you well know. And this is the upper part. This is the part driven by solar energy. But it's overlying the part that is significantly influenced by internal energy. And plate tectonics and underwater volcanoes and all sorts of factors that go on deep within the Earth have, for the last 4.5 billion years, been moving the tectonic plates around, been releasing microbes into the overlying ocean, or in fact, many people think that the interface between volcanoes underwater and the overlying ocean was in fact the environment or the crucible within which life actually evolved on the planet. It's a challenging hypothesis, but it's pretty intriguing. So there are many processes here that we could talk endlessly about, but the main point is captured in a sense in this image. And that is, here is one variable, sea surface temperature, and it's an annual cycle. We're just repeating the same video clip annually. So that's northern summer, winter, northern summer, winter. And look at the interfaces between the different colors. Look at the complexity of all the eddies and all of the complexity, and even the equatorial countercurrent here, and all the complexity here on next to the continents. That's only one variable. It's temperature. It's very important, and it's only the surface of the ocean. But look at how dynamic it is, and look how complicated it is. Now add 200 or 300 variables, and you have a complexity that's probably proportional to n factorial. Well, when n is 100 or more, n factorial is a big number. And so the ocean is unbelievably complex. It's not going to be something where we can casually go out, as has been done in the past, in a ship, run your experiments in a particular place for a week or two, go somewhere else and do experiments in another place, bring the data back, and interpret the ocean. It can't be done because it's like crossing a stream. They say, well, you can never cross the same stream twice because the water's always flowing. Well, the ocean is the same way. It's constantly moving. You do one measurement in one place, you go someplace else. While you've gone someplace else, the ocean has changed. So not only is it complex, it's immensely dynamic. Why is it so important? Because food on the continents is actually correlatable with variations in the sea surface temperature. Look carefully at this diagram. It's not quite as clear as I'd like it to be for you, but this is the El Nino, La Nina cycle here. Red is El Nino, blue is La Nina. So here's sea surface temperature. So warm colors are warm, or red is warm sea surface, blue is cool. Here's the timeline. It's a cycling video. It's 1983 to 1998, and then it cycles again pretty fast. But what's most important is that here, the vegetation index, bright green is growth of vegetation. Brown or olive green is dieback of vegetation. So look at the patterns on the continents and look at the patterns in the ocean. And I'll guide your eye for the first, initially, to the Horn of Africa. There's only a small number of times when it turns bright green and has plenty of food for everybody and enough to export. It's rare. It's very rare. But look how it correlates. You can see out of one eye or the other that it turns bright green in the Horn of Africa when there is something going on called El Nino in the Central Pacific, half a planet away. The whole planet is a single system. The ocean is the driving force behind it. And it's extremely important to realize that droughts, patterns of floods, all sorts of patterns on the continents are actually determined by the dynamics of the ocean. And we don't understand that very well. That's at the broadest scale. So the oceans are fairly important if you relate the growth of food to the health of the human race. And just to give you a quick view of what North America quickly looks like, these are some of the patterns. So El Nino, La Nina, it does change. You're probably all aware of this. I'm just reminding you of this particular. Now, let me shift gears just a minute. I've talked about the ocean and the water. Let me talk to you about the rocks. Here's a picture of the age of oceans. The youngest rocks on the planet are all along here, and in many cases, notice it runs right through Iceland, which is a volcanic island. The youngest rocks here, the oldest rocks in the ocean basins are about 200 million years old. So here in the Western Pacific and then the Western Atlantic are rocks that are about 200 million years old. The planet is 4.6 billion years old. So the ocean floor itself is only a small fraction of the total, in terms of its age, is only a small fraction of the total. That's because plate tectonics corresponds to the delivery of molten rock continuously here and spreading at about the speed your fingernails grow. All of you have been exposed to plate tectonics, but be aware, now watch closely because I'm going to substitute a plate tectonic framework for that. I'll go back a minute. You see very clearly that the patterns of the youngest rocks and the oldest rocks in the ocean are directly related to the boundaries of plates. So the dynamics of plates and how they move actually controls not just the arrival of molten rock, but the formation of submarine hydrothermal systems and the formation of major earthquakes and the formation of volcanoes erupting. 70% of all the volcanic activity on the planet happens underwater. Why do you care about volcanoes? Oh, we'll come back to that. I hope by the end of this talk you will care more about volcanoes. Okay, so looking at the plate tectonic, if you notice the Juan de Fuca tectonic plate up there, it's a pocket-sized plate located just off the Pacific Northwest, not far from Seattle, which is a sort of a nice thing. This is the Vancouver Island. This is Puget in the Straits of Juan de Fuca here. And this is the edge of the continent in terms of the coastline. This is the edge of the continent in terms of the continental shelf. And this is the tectonic plate, which is moving this way, compared to the North American plate, which is moving this way. So you've got a situation like this. And then you've also got Pacific plate moving this way. All right. Well, what a convenient thing to do. I mean, if you wanted to make a laboratory of something, you wouldn't want to do the Pacific plate yet because it would cost the equivalent of 25 trips to the outer solar system. Whereas, if you took this pocket-sized plate and you said, why don't we turn that into a laboratory? This is the thing that Rita bid on. I don't mean bid. Rita supported this, and I will allude to that. I just wanted to show you, just as a cross-section, here is the northern end of the Juan de Fuca tectonic plate. It's complicated in some ways, but it's simple in others. Now, what I'm going to do is take a knife, slice through it, and I'm going to roll that up so you see what a cross-section of it looks like. And I've stuck just for convenience, the patterns of circulation here in the deep mantle are actually reflected where there's rising molten rock that collects here, and then the plates pull apart in such a fashion that actually creates new tectonic plates, and that's where all the volcanism is on the planet. That's where the young rocks are. That's the setting in general. You have plate tectonics and you have water movement, and that's the ocean basins. 70% of the planetary surface is the ocean basins. Let's take a quick look at the future, and this is extremely important because emergent technologies that are being paid for outside of the world of oceanography are available to oceanographers under the right circumstances. If the right circumstances consist of converging these kinds of new technologies, which I'll show you in a minute, we would experience an exponentially increased capacity to understand the ocean in ways no one has ever imagined before. Why do I say that? Well, here's a couple examples. There are many. Each of these represents a new wave in a sense, in that power development from the ocean in many ways, all the various ways that you develop power in the ocean, are taking leaps and bounds. It's slow. It's not been heavily invested in other than oil and gas and things of that sort. But rapidly we're developing power. The work that's going on in robotics is unbelievable. The rate of change of the capacity to have machines do things is rapidly changing. Each of these is on a kind of a Moore's law curve of increasing capacity. decreasing cost, and miniaturization. Each one. Ecogenomics, the capacity to do genomic analyses remotely, has been pioneered by Chris Scholin from the Monterey Bay Aquarium Research Institute. And we now have ways of doing genomic analyses without anybody nearby. Everybody here is aware of digital imaging. You've probably got one in your pocket. 15 years ago, you could not take a picture of somebody and send it to your grandmother in seconds. Now, you don't even think twice about it. The rate of change taking place here, driven outside oceanography, is giving us sensors that you wouldn't believe. This part, optical fiber, it's possible with a fiber of this type and tiny little threads inside it, it's possible to transmit terabytes per second of data routinely through a single fiber pair. And you can put as many as 10 fiber pairs in a given cable. So the capacity that we have for communicating as well as delivering electrical power into a remote environment like the floor of the ocean is unbelievable. The world is girded right now by hundreds of thousands of kilometers of fiber optic cable through which all of us communicate. If you communicate with anybody who's not in North America, you're communicating through fiber. You're not communicating through satellites. And then cloud computing. I don't need to say much about this. If you've ever done anything called the verb to Google, it's actually derived from the ability to do a search using that unbelievably fast computational power. And anything that you inquire about, you probably get something like 500,000 answers to your questions in something like 1/10 of a second. And that's just what we're exposed to. Some of the models that it's going to take to model the entire planetary ocean are much, much, much more demanding. The speaker yesterday that spoke about the astronomy, are taking advantage of similar kinds of capabilities. And then nanotech, I'm in this group, I won't try to talk about nanotech, but the promise is still out there in front of us, but it's coming much more rapidly. All of these, when they're put together in a form that allows us to have high bandwidth and high power, can translate into a situation in which you may recognize this now as a Juan de Fuca tectonic plate, and this is the fiber optic cable that was supported by the National Science Foundation. And that's my premise here, is that delivering power and bandwidth into the ocean will dramatically accelerate the rates of technological development and innovation. Dramatically. Imagine you would never consider taking a job at an institution, whatever it is, whether it's a university or a company, if you didn't have internet connectivity, high bandwidth, and electrical power in your labs. Now we have it in the ocean. It's available offshore where no one is. So a little of the history. When we first started talking to Rita, this is what we had in mind for, each one of these is a particular node. All of the, it was, I have to say, overdid it. She still bought it. She said publicly in 2002, in front of a lot of politicians and admirals, we at NSF are going to build this Neptune system. And she even mentioned John Delaney as associated with it. I'm forever in your debt. So here is my beginning of paying the debt. This is the lady that when she was at NSF, I don't know what they do at NSF, but I was raised Catholic, so I think she blessed this thing. And the next thing you know, a decade later, she was gone by the time the money arrived. But the program that I'm talking to you about was estimated to be about $150 million. And that's in fact what we received. And we have now, as of 2.5 months ago, have completed this system. And for that, I will always be in your debt, Rita. This is the program. Those sites are located, and I'll show you a quick overview of the entire thing here. Yes. So there are high latitude sites, meaning high latitudes, and those are satellite linked, and they are moorings and gliders, platforms that can move through the water. And they are making measurements of the air-sea exchange at those high latitudes, which is crucial to modeling the entire planetary ocean. On the East Coast is something called the Pioneer Array, right off of New Jersey and Cape Cod. And on the West Coast is the one that I am the most familiar with and have spent some time trying to develop, and that's this diagram that I just showed you. Two cables, the Canadian cable, we originally were working together with the Canadians. In 2001, the United States drifted into a couple wars, and the Canadians went ahead and funded this thing, so they went quickly forward. By 2009, we received the funds for this, and as I said, we have just finished building it. And this is what the Northeast Pacific, now there are more assets right now in the Northeast Pacific in terms of doing ocean science than anywhere else. And these are the cables. These are the nodes where individual studies can be done, same for Neptune, Canada. And the entire area is literally wired to look at the Juan de Fuca tectonic plate. This has been almost 20 years coming about. So the primary infrastructure, let me just very quickly show you this, and then we'll go from there. The primary infrastructure is defined as the cable that comes from shore. We used a directional drilling technique behind the beach front in Pacific City. We drilled down, out a mile into water depths of 20 meters, two pipes, and then had a gigantic ship come in. This thing is about 500 feet long, and pulled the cable from the ship through the holes into the shore station. So we had the basis of laying 900 kilometers of fiber optic cable. That was done in 2011, all the cable links there. In 2012, we put in the primary nodes. Those are pictures of them. That one's trawl resistant. This one is for deep water where they don't fish right now. Here is the foredeck of the cable ship, and that is one of those. These are normal human beings here. This one here. And so it's a pretty sizable unit. And that's the exact same item in 1.5 miles of water on the seafloor, on top of an active volcano. And here's the final product, which is the RSN primary infrastructure. And it is the Pacific City is the shore station, Oregon. There are 2 backhauls to Portland, and then it's connected to the internet. One cable goes all the way across the tectonic plate to a place called axial seamount, which you'll hear a little bit more about. And the other one goes down to the base and down, and then comes back up the slope. And this one is looking at earthquakes and activity at the edge of the continental shelf and the plate coming together. So on one side, we're looking at the way the plate comes apart. On the other side, we're looking at the way the 2 plates converge. Oh, and at these sites, this cable has 10 kilovolts of power and 10 gigabits per second bandwidth, readily distributable. And then these systems step that down to secondary nodes, which have 375 volts and 1 gigabit per second. So we have distributed capacity to go out to like the arms of an octopus, and each arm can handle a lot of bandwidth and a lot of power. So we have instruments then that can be daisy-chained on those. And the secondary infrastructure therefore is what we put in just this summer. I spent 3 months at sea this summer on this ship. I'm quite fond of it. It's the Thomas G. Thompson. This arrangement here is a remotely operated vehicle called ROPOS, R-O-P-O-S. It's a Canadian vehicle. And with that vehicle, we were able to put down secondary nodes. These are the ones that take the power from the primary node and are then clustered around them will be the instruments. Okay, we did 17 of these, and this is cable that we lay on the seafloor. We drive the ship along the path, so we connect the nodes on the seafloor to the secondary nodes, the primary nodes to the secondary nodes. And we laid something like 30 kilometers of that this past summer. That's what one of the secondary nodes looks like. And we did 17 of those junction boxes deployed and working today, all working. And for those of you that have sort of a scientific and or engineering bent, here is what a primary node, a functional block diagram would be. The primary node is here. Each of these is that orange cable that I was talking to you about. In some cases, it's as much as 5 kilometers long. And here is what that looks like on a reel. And we put that on underneath the ROV, and we would drive along the path right over volcanoes, right over faults, right over everything, making sure that we knew exactly where everything went. And so that's what it looks like slung underneath the ROV. And these are the instruments. By the time it's in the water, which it is now, it's well over 100 instruments. It's actually 140. And I'm not going to drive you into the ground by talking about every one of these. But for some of you, let your mind or your eye look over these, and you see what a variety of instruments we have, all of which are now remote, all of which are now working, all of which are now sending data back, all of which is available soon to the public. Now, you may not be that interested in seismometers, or you may not be that interested in pictures of tube worm beds, or you may not be interested in one form or another. But there's enough diversity and enough multiplicity here that we feel like it's going to appeal to many different folks in many different ways. And what we're seeking are those who can integrate. Now remember, there's a big piece here which I mentioned early in the talk. All of these data are going to be made available to all of the people who have access to the internet all of the time, in real time. All of the people, all of the data, real time, all of the time. That's different. That's a game changer. How do we do? One of the things I worry about is what's this going to set off? Is it going to be more difficult than it is positive? Because we're not trying to clutch the data to our bosoms and say, no, 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 that's mine for the next 2 years. This is what the world of oceanography has consisted mainly of, I have to say, tall white males going to sea on a cruise, collecting the data, driving as grad students to distraction, getting all the data, bringing it back, coming ashore, holding the data for 2, 3, 4, 5 years, publishing it when they felt like it. And that has slowed the whole system down. So we made a decision right in the beginning. No, all the data to all the people, all the time. What the consequences of that are, we might talk about. But this is what the instruments look like. Some of them are bold and new. Some of them, like seismometers, are well established. This is a hydrothermal site, actually with instruments in it. Rita, I think you dove on a couple of those, didn't you? And here's one of the innovations. We have a two-legged mooring with a platform at 200 meters. That's this thing you're seeing over here, 200-meter depth. And we can control this instrument package from shore with great precision. We can decide exactly how far up it goes, when it comes back down, what the instruments are on it that are working on and off, and how frequently they're sampled. We can change all that from land. And all the data comes back all the time to all the people. Complementary to that is this one here, which is from the seafloor up to 200 meters, and it's constantly moving up and down as well. So these two are meant to complement one another, and it allows us to look continuously at how the ocean itself is changing through time, and we control it all from land. So here's what the continental shelf looks like. Now down here in the corner, I don't know how many of you can see this, but down here in the corner over here is where we are. So there's Pacific City, I showed you that. So we're looking at the deep water to almost continental shelf here, or almost the continent, change in elevation. And that's what this diagram here is. It goes from 2,900 meters to 25 meters here. The cable snakes all the way across all these. There's the primary nodes with secondary nodes around them. And some of these moorings that I just talked to you about, there and there. So we've wired the continental shelf in a way that no one has ever done anything like. The Canadians didn't do anything like this thoroughly. And all of it's out there, and all of it's working. The data is going to be handled by Rutgers. So we are waiting for NSF and Rutgers to come together with the ability to manage the data. But we're storing all the data in Seattle, and I'm happy to relate that as of Monday this week, all of the seismic data is now available to all the people all the time. And so this is the essence of what we've done in the last summer. All of these things are in place. That's an example of 3 of the instruments in a single hydrothermal site. It's really, it's really exciting for me. I have to be honest. So what could you do with this? All right, that's great, Delaney. You put a bunch of trinkets on the seafloor and you spend a hell of a lot of money, which we could have spent designing tests for solving diseases. But maybe this is a long-term investment in sources of microbes that we don't even know about. When a volcano erupts, the microbes that are below the seafloor, which no one has ever seen before, will be released into the overlying ocean. So, Marguerite, I just wanted to say a word to you. I loved your talk yesterday. And I'm an oceanographer, so I heard what you said differently. You used the metaphor of a grain of sand in an oyster as reference to some irritant. Having listened to your entire talk, in my view, that was the setting that, in the form of your presentation, produced a pearl of great worth. So I wanted you to know that an oceanographer sees things differently, but I'm building on your metaphor. That's what oceanographers do. So someday we should talk about irritants becoming pearls. What can you do with a system like this, you ask, which would be an irritant if I hadn't spent the last decade thinking about it? Well, one thing is, instead of having one ship in one place at one time, which is about all you can do, or a satellite that only sees the surface of the ocean, suddenly we've got many locations in many different places working all the time and all the data coming ashore simultaneously. So we can simultaneously conduct research in each of these areas plus another 10 at no cost to anyone else. Indeed, better than no cost. The data from one type of study could indeed inform discoveries related to another kind of study. So there are many, many diverse capacities that are only now just begun. And I will say that this cable observatory is not the end. This is just the beginning. Almost every country, I've been to 14 countries in the last 4 years. Every single country wants to know what we're doing, how much it costs, how can they design it, what can they do with their system, and would we help them? There will be many, many more of these. I don't know what their nature will be, but there will be many more of these. For fiber optic cables, the costs are dropping. The whole capability of being present throughout the ocean without having to be there is a game changer. Okay, so what could you do? This is 2 years worth of earthquakes on the Juan de Fuca tectonic plate. It's not as if we're going to sit around and it's not like waiting for the grass to grow. Something's going to happen while we're out there. Many, many things are going to happen while we're out there. Only this is an example of the earthquakes. And every single one of these earthquakes, we have evidence. It's fuzzy evidence right now, but evidence that when the seafloor cracks or when there's any kind of a disturbance, microbes from below the seafloor come rushing out from the new cracks, driven by the hot water that's released, and they're there for sampling. We've done this 3 or 4 times now. We're pretty good at it. But we never know when it's going to happen. Well, all of a sudden, we've wired a piece of the ocean, and we're going to know ahead of time when it's going to happen. So here's a scenario. That's axial seamount there at the end of the terminal line. Here's earthquakes. This is a pattern of earthquakes that we have from earlier. Each one of those is proportional to the size of the earthquake. And we decide that axial seamount is erupting. We can tell that by something known as harmonic tremor. And we send in the troops in the form of remotely operated vehicles, or actually autonomous underwater vehicles. They fly into the eruptive plume, take samples, and eject the samples to the surface to be picked up by, what else? A drone. We're pretty good at using, this is an academic drone, so it doesn't look nearly as threatening. But these samples are from microbes that have just, less than 3 hours before, come out of the sea floor, and we can return them to laboratories in nearby cities for analysis. What kinds of discoveries are on our threshold here? What could we do with this? You remember the polymerase chain reaction came from the polymerase, which came out of a 75-degree Yellowstone vent. What else is hiding that we could use for the benefit of humankind in these systems? We don't know yet because we haven't explored it. Here's another approach. The Chris Sholin's approach to doing genomic analysis remotely, fiber optic cable driven. Each of these little laboratories is about the size of your kitchen garbage can right now, but in another 5 years it'll be half that size. Something happens. It could be a harmful algal bloom. It could be anything that takes place. It could be a volcanic eruption, changes the conditions in the environment. You turn on the pumps and pull in the bacteria and the plankton, and you hit the analysis button, and the genomic character of the smallest organisms that are in the system, the base of the food chain, basically, is immediately rendered for you on land 200 to 300 kilometers away from the nearest human being. You've gotten the data. How many of you remember, everybody I'm sure remembers 9/11, how many of you remember 9/7, 2001? On 9/7, 2001, some doctors in New York City removed the gallbladder of a woman who physically was in France. I do not know why the woman agreed to do that, but it was a success. Well, that was a decade and a half ago almost. What could we do offshore with power and bandwidth in terms of running real-time laboratories in real-time environments with no humans in sight? What could we do? What could you do? Many of you younger folks, this is opportunity. Use your imagination. We have the basis for bold new steps in terms of how we study the ocean. Here's something I would call Imagineering. I'm not an engineer, but I'm Irish, so I have an imagination. It's a network of robots working in concert, like basically fish. The orange balls are the navigation balls. The yellow balls are the sensor balls. They have about 24 sensors in each one of them. And the green balls are the communication balls that go back to the fiber optic cable in the distance. And it's searching for something. There it finds a black smoker. I don't know how well you can see that, but it finds an active black smoker, and suddenly you're controlling this on shore by managing the location of all of these things and turning on and off the sensors. This is doable. We have the bandwidth, we have the power, and we have the assets to do this. And if we have the drive to understand what's going on in 4 dimensions simultaneously from 20 different variables, we have the capacity to do that 400 kilometers away from the nearest human being. This is doable. This is doable now. So one of the things that's of interest to a lot of people, including my colleague Kendra Daly, who listened to me endlessly talking about how exciting erupting underwater volcanoes were, and she said, well, you know, Delaney, yeah, volcanoes are cool, but what about the overlying ocean? You can't erupt a volcano without disturbing the ocean. I said, what do you mean disturb? She said, well, it's going to change the ocean. And of course she's right. So we came up together with this idea of drawing a box around the most active volcano offshore, axial seamount. And in this box, we will characterize, prior to the eruption of this volcano, we will characterize almost everything that we can characterize about what's going on in the water. So we have a control volume in a natural laboratory that's available to anybody to see what we're doing. Here's an example of what that might look like. This is sea surface temperature. Sea surface is right at the dark blue sheet. We go through it, and I'm pretending that you can then see. So you have all these sensors moving about, under control from land, sending data back continuously. You have milk run patterns in these sinusoidal curves. Watch this particular one. I can pull this over and stop it right there. That's an AUV, an autonomous underwater vehicle, designed by folks at Woods Hole. And it's a cute little unit that can measure about 20 different things simultaneously, and then go and plug in and download its data.
How big is that, John?
It's about that high, but I want one that's about a third that size. Well, actually, I want 3. Good. Yes, let's discuss that. Right. It's not. I'm not a used car salesman here. I want a brand new. Anyway, so why do this? I mean, because for the first time ever, we're on the threshold of being able to characterize from the outset, before, during, and after, what happens when an underwater volcano erupts into the overlying ocean, like it's doing just now. And with all these sensors in the area, and with, I can see it here somewhere, there it is. That's one of the little vehicles. It turns, and it knows enough to come toward this thing, go through it, and then turn around, and it'll come back through it. And there's another one up here. We can quantify all the heat, all the chemicals, all the microbes, everything that has come out of the sea floor as a result of this volcanic eruption. Why am I so excited about this? Because the seafloor of this caldera on top of axial seamount is now rising at 60 centimeters a year. Imagine if that happened to your house. You would move out. Well, if you lived on top of axial seamount, I recommend you move out, because in another 2 years, year and a half, it's going to erupt. And for the first time ever, human beings are hardwired into this eruptive system under 1.5 kilometers of water. Never before have we been able to be there when something like this happens. What are we going to discover? I don't know. What will we sample? Microbes, of course. Chemistry, of course. We will understand one of the most fundamental processes that's happened on the planet for the last 4.5 billion years, the eruption of a volcano into an overlying ocean. That's how the whole planet formed. That's why continents are there now, because of that whole continual process. I find this just enthralling. And how will we look at the data? Think about this. You know what a hologram is? Well, these young ladies are looking at the way that we will begin examining data from the oceans in time, and talk about it and move it around. It's sort of science on a sphere, if you like, but a holographic sphere. And you can project whatever the data is you want. And you can begin all sorts of things. This is just around the corner once we have the massive data flow, because we have the computational power to do this type of thing now. We can look at entire marine ecosystems and all their variables in a fashion like this. This is really important. So we are starting a website. We will be tracking daily what happens on axial seamount. The input on the left is everything from student videos to 3D modeling. On the right is output to the public, to the community, to whoever, theaters, exploratoriums, whatever. So this whole thing will become one of the centerpieces. Now, it's just because it's so exciting and it's on the threshold. There are many other facets to talk about. Now then, one of my great pleasures is what this lady said. It's just a fantastic statement. Please read it carefully yourself. If there's poetry in my book about the sea, it's not because I deliberately put it there, but because no one could write truthfully about the sea and leave out the poetry. God, I wish I'd known this woman. So, Pablo Neruda, it is born. Here I came to the very edge where nothing at all needs saying. And everything is absorbed by the weather and by the sea. And the moon swam back, its rays all silvered. And time and again, the darkness is broken by the crash of a wave. And every day, on the balcony of the sea, wings open, fire is born, and everything is blue again, like morning. The ocean is about rebirth. The ocean is about regeneration. The ocean is about everything that we need for this planet to continue to be as effective a living place as it is. And Neruda had an unparalleled skill at expressing the magic of that. Now, from the point of view of humor, you know who Dave Barry is. There's nothing wrong with enjoying looking at the surface of the ocean itself, except that when you finally see what goes on underwater, you realize you've been missing the whole story. Staying on the surface all the time is like going to the circus and staying outside the tent. This is true. I've spent a lot of time underwater. A lot of time underwater, deep underwater. Here's an example of a hydrothermal system. This plume for this tube worm, this neck here is actually about the size of my finger. High definition video, hot water flowing from below. The community is living, it's thriving in 17 degrees centigrade water. What else is living in there? We don't know. Can we culture things there? Can we actually do experiments in situ? What can we do with this? And here's one, forgive me for indulging myself here. This is the Moldau by Smetana. How do we bring this to the public? How do we talk to the public about how important the ocean is and how exciting it is, and capture the ideas of young people, to capture their creativity early on? There are many ways, some of them through art, some of them through science, some of them through storytelling. I'm sure Smetana never once in his whole productive life ever thought about a tube worm, or that his music would be used. Anyway, poor guy. So it's about the time domain. We finally understand the geometry of the oceans well enough so that we can begin focusing on how the time domain changes within the oceans. And I just love this piece by T.S. Eliot from Burnt Norton, one of the four quartets. Time present and time past are both perhaps present in time future, and time future contained in time past. If all time is eternally present, all time is unredeemable. This is the tricky part. That was part tricky. What might have been is an abstraction, remaining a perpetual possibility, only in a world of speculation. What might have been and what has been point to one end, which is always present. Footfalls echo in the memory, down the passage which we have not taken, towards the door we have not opened. My words echo thus in your mind. This captures the time domain, it captures the variations, it captures the complexity that we have at looking in really complex systems and complex poetry, I have to admit. It just is powerful. We need to bring these things to the public in the broader way. Science is just one part of our cultural heritage, and we need to make sure that it's cast in that regard if we would reach many people. We need to be guided as best we can by the past, but we're attempting to envision the future. And it's very difficult to do that. What might be one of the more exciting pieces? Well, here's a quote from Kennedy, which I kind of think is cool. It is an interesting biological fact that all of us have in our veins the exact same percentage of salt in our blood that exists in the ocean. Therefore, we have salt in our blood, in our sweat, in our tears. We are tied to the ocean. And when we go back to the sea, whether it is to sail or to watch it, we're going back from whence we came. But the future, these kinds of plumes were detected using the Hubble telescope on Europa, the second moon of Jupiter. The possibility exists that there is indeed a shallow ocean, an ocean shallow beneath the ice, and that within the lifetime of our children, we will explore it. It's an ocean, and I would paraphrase Hillary Clinton. When it comes to life on a planet, it takes an ocean. Now, what we do with the ocean we have on this planet, and how we learn how to work in it and how to do it remotely, is going to inform the way that we search for life elsewhere. Because this ocean on Europa, by best estimate, is about 100 kilometers deep. And it's below 2 kilometers to 6 kilometers of frozen water ice. And it's a bad place to be. It's a vacuum. The surface of Europa is a vacuum. It's bathed by radiation from the magnetic field of Jupiter. So you would freeze to death before you died of radiation poisoning if you stayed on the surface. On the other hand, if you can get down into the thing, maybe 20, 40, 60 years from now, we'll be smart enough to know how to survive under those conditions. A couple 100 million years ago, our ancestors did. We can learn. So it's about marine ecosystems. It's about understanding marine ecosystems. It's about understanding the role that the ocean plays in the well-being of those of us that live on the continents. And I look forward to the day when there will be major cities that are not necessarily on land, but are actually floating cities in international waters, moving about under control, submerging when they need to, farming when they need to, and simply living off the ocean, and maybe living within the ocean. Thank you very much.
Thank you, John.
I think I talked too long.
No, I invited John to speak to us. Yes.
How well is the field funded?
For a brief shining moment, we had enough money to do what we just did. But what's happening now is the world of oceanography is not a cheap world. A ship itself costs something like $35,000, $40,000 a day. A remotely operated vehicle like the one I showed costs something like $25,000 a day. So together, you're talking $70,000 a day. That's why in the long term, these kinds of remote systems will pay off. Although the initial investment in the cable was high, for 25 years, we expect to be able to do science only by visiting periodically with the ship. We don't have to have the ship there the whole time. So it's a big step forward, and I think that we are, my personal opinion is that ocean science on this planet deserves a budget that's comparable to outer space. We are much more dependent on inner space than we are on outer space, frankly. And I'm excited by exploring the cosmos. But within the next 40 to 60 years, the population is going to go somewhere close to 10 billion on the planet. And we are still dependent on this ocean to keep us. 50% of the oxygen that you're breathing this moment comes from microbes or single-celled animals or plants in the surface of the ocean. Most of the CO2 that we have generated, about half of it, has been absorbed by the ocean. There's more heat in the upper 2 meters of the oceans itself as we see them than in the entire atmosphere. So to think that although our weather comes from the atmosphere, we tend to think of the atmosphere as being storm-driven. In fact, it's ocean-driven, and the storms are the result of that. So the engine of the planet survivability, planetary survivability, is the ocean. We need to understand it far better than we do. So I would say we're underfunded by a factor of 5.
Well, in the Midwest, or places where they do not have access to an ocean.
They will now, by the way.
Well, is there right now are there curricula developed to encourage young scientists to go into this field even though they do not think of or see an ocean before,
The problem is academics don't come out from the ivory tower and actually talk because, the droughts that are besetting the Midwest are the result of the oceans. That's not the Midwest that's in trouble. That's the change in the patterns. And remember the Dust Bowl? Same thing. Ocean patterns, ocean circulation actually precipitated that setting. And so it's directly related to the behavior of the ocean. So if I lived in Kansas City, which I probably never will, but if I did, if I had a phone, I could call people there, I'd say, think about oceans. Begin to plan on oceans and try to turn the kids on. And that's why I think this cabled observatory with the capacity to send real-time information about all aspects of oceanography anywhere that the internet goes is our equivalent, inner space equivalent, to what people can do to astronomy. You can always look at the night sky, right? If there's clouds, you can't, but everybody has access to the night sky, so they see the cosmos and they can dream about stars. But you're right, people in Kansas, and there are still people who live there, don't think about inner space, but they should.
Can I ask a very quick question before, I don't know if this is on or not?
No, it's not.
I can hear you very clearly.
Can you turn this on? Somebody
No,
turn
go
it?
ahead.
No, but
Just go ahead.
Okay.
No.
So, have you given a TED Talk?
Yes,
And you have given it how many years ago?
2010.
Okay, we need one more. No, seriously.
What are you doing this afternoon?
I am not a TED person. I just gave one, and they keep coming after me. But the point
Well, I can see
is-
why. You give a really good talk, lady.
Oh, thank you. I didn't think I gave a good talk. Thank you very much.
Well, the talk yesterday by Nina was just stunning. That was,
Yes.
I mean, I'm enthralled by the quality of the science at this
Thank you.
meeting. It's just really a delight.
Yeah, thank you very much. But honestly, there are so many kids who watch those things. I am just absolutely amazed of the number of people who write me, the number of the people who have watched it, and now it has gone all over the world. It gets translated into all languages, etc. So I will contact them, and I think you really should give one more, and you should say some of the stuff you said at the end. We need young people to go into this field.
Give my warm regards to Chris Anderson. He's an
Amazing guy.
Yes, he is an amazing
Yes,
guy.
yes.
Thank you, John.
It's a pleasure.
Delivered.